Nothing else.
Okay, so we are now in the colloquium for this semester with Valentino Tosatti. He will discuss about metric limits of Calabial manifolds, which is basically the subject of this workshop. So,
okay, thank you very much. Thanks a lot for the invitation, and it's really a pleasure and an honor to speak at the colloquium. And I should also apologize, first of all, to the colloquium participants, because this talk is going to be very much related and maybe too elementary for those people. Anyway, it's very related to the topic of the workshop. Maybe I should also apologize to Pelham Wilson for plagiarizing the title of my talk from one of his papers. So it's the title of actually a survey paper that he wrote a few years ago. Since it's a colloquium, I'll start with some really basic introduction to first Calabi-Yaus. So to set up some notation, maybe remind you or briefly recall the basic definitions. X in this talk will always be a compact complex manifold. So by this I mean that it has no boundary. I will not discuss manifolds with boundary. And it is X. So being a complex manifold means that it's like a usual manifold covered by a bunch of charts, but each chart is like an open set in Cn instead of Rn. And then when you have two which overlap, the transition function from one chart to the other should be holomorphic. So this map here is holomorphic. And this gives us n. Yes, here it's going to be the complex dimension. So that's half of the real dimension. So if you view X as a real manifold, then the dimension is 2n. And the fact that you have this locally like Euclidean space Cn means that you have local holomorphic coordinates. Which I'll denote exactly like the one in Euclidean space, z1 to zn near every point. I will promise I won't use them too much, but maybe just a little bit at the beginning. And I study complex geometry, so complex manifolds, and then you need a metric to talk about geometry. So G is going to be a Hermitian metric on X. So this is just the analog of a Riemannian metric, but it has to be on each tangent space a Hermitian inner product. Each tangent space now is a Cn. So and of course every complex manifold admits Hermitian metrics, so you always have these. And so on each tangent space is a Hermitian positive definite. So in particular, if I look at the G of so the tangent vector d by dzi. This is like a complex tangent vector. And being Hermitian, I have to take the conjugate here. This one here, which I call gij bar, at some point. This is going to be an n by n positive definite Hermitian matrix at each point. So at each point on the manifold, you compute this inner product, and you get a positive definite n by n matrix. I and j bar go from 1 to n. And I define very conveniently a two-form omega. So this would be I. So I'm using this summation, Einstein summation convention. So this omega is a real 1-1 form. I explain now. So I wrote this expression here using the complex coordinates, and I put the square root of -1, so that when you take the conjugate, this changes the sign. But G is Hermitian, so when you conjugate, it's the same as the transpose. And when you conjugate this, the bar flips, and you flip it back, and the minus sign comes back. So omega is real, and 1-1 form just means that in these local coordinates, there is one dz and one dz bar. So it's in particular a two form of a special type. And G is, in some sense, equivalent data as omega. So if you know G, you get omega, but conversely as well, the coefficients are the same. So I will very often confuse and blur the two, and probably I will use omega most of the time to talk about the Riemannian metric or Hermitian metric. Okay, so we'll say that this G is a Kähler metric if the exterior differential applied to this two form is 0. So in local coordinates, perhaps easier to understand is just that if you take partial derivatives, say, of the metric with respect to this holomorphic coordinates, then you have this symmetry property for all ij and k. So it's just this condition, we can think of it as, in fact, a partial differential equation or a partial differential relation. And it turns out to be a really extremely nice condition to put. Maybe I won't dwell on it too much, but it really says that the Riemannian structure of G and the complex structure on the manifold are compatible in a deep way. So some examples of complex manifold in Kähler metrics. As I said, everything will be compact in this talk. So when n is equal to 1, that would be the first case to look. So we are real two-dimensional manifolds. So X is a compact Riemann surface, compact orientable Riemann surface. So Riemann surface just means the complex manifold dimension 1. And conversely, it's a really nice theorem that if you have a compact orientable two-dimensional manifold, then it admits the structure of a complex manifold of dimension 1. So these are the same as orientable two-dimensional surfaces, and I assume compact, but you don't really need it for this theorem. And if in this case, the condition of d omega 0 is always satisfied because this will be a 3-form on a 2-manifold, so it's always 0. So here all Hermitian metrics are Kähler. Okay, so the next example is the projective space, so CPN. So it's just a Euclidean space, remove the origin, the 0 vector, and mod out by C star, which acts here just by multiplying all the components at the same time. So this is a complex manifold. It's not hard to write down an explicit atlas with the n+1 open sets. And here there is a very nice and explicit Kähler metric, which is called the Fubini-Studi metric. I can even write down the formula. Gij bar is given by di dj bar of log of mod z squared. So this one here, sorry, I didn't define this. Say ddzi, ddz bar j of log mod z squared. So this would be the formula on Cn+1 minus the origin. And then you prove that it's actually invariant, so it descends. So if you expand this expression, you get a nice Kähler metric on projective space. And in fact, this metric is Einstein. So as we will say later, the Richie curvature is a constant multiple times itself. Or maybe I should call it GFS. And the last general source of examples that I will just mention is when X is described by polynomial equations in projective space. Maybe like this. So here the PJs are homogeneous polynomials. The degrees can be different. And so the common 0 locus of these polynomials is well defined because the polynomials are homogeneous. So that the 0 locus is well defined, it's preserved by this action. And of course, you need to assume that it's smooth. So if you just write down some polynomials, it may not be a manifold, but at least for generic choices of polynomials, this is smooth. And if I restrict the Fubini-Studi metric to this X, then this is a Kähler metric. So this gives you a lot of examples, and these, of course, are nothing but smooth projective algebraic varieties over C. So these are all particular examples of Comper-Kähler manifolds with the Fubini-Studi metric. Okay, so I want to get to CalabiYau, right? So briefly, I'll tell you about the Ricci curvature. So if G is a Kähler metric, there is something from Riemannian geometry which is called the Ricci curvature of G. This is just a part of the whole curvature tensor. The curvature tensor is something which has 4 indices usually, and if you trace 2 of them, you get the Ricci curvature. It contains partial information about the curvature, and it looks like the metric. It's, again, a tensor with 2 lower indices, I and j bar, and it's given by the very nice formula, Ri j bar is locally given by minus Tci. Tc bar j of log of determinant of the metric. So if you take the determinant of this matrix at each point, you get a smooth positive function, so you can take log, and then you can take derivatives and with a minus sign. Notice the resemblance with this one. So this formula here is really the key to a lot of the fundamental results about complex Kähler manifolds. In particular, what you can do first is like here, you turn this tensor into a form. So if you let Richie of G or Richie of omega, I will use both notation to be the same. Then this is a closed real one-one form. So closed means as for omega, the exterior derivative is 0. And furthermore, if I have 2 of them, if G prime is also Kähler, another Kähler metric, and I compare the 2 Ricci curvatures, or maybe the 2 Ricci forms, I can write this globally as 2 derivatives of log of the ratio of the determinants. Where here, this strange notation of the del is where you split the exterior derivatives into two parts. The one which turns a PQ form into a P plus 1 Q form and to a PQ plus 1 form. Here you can change this to D if you wish, because both of these D and D bar square to 0. And the ratio of the determinants, so the determinant of a metric is not a globally defined function. When you change the chart, the determinant changes. But the ratio of 2 determinants is globally defined. So this is a globally defined smooth function. So you see that the difference of these 2 closed forms is exact. And therefore, you get well-defined class in cohomology, which is the closed forms modulo exact forms. So I'm going to, for now, divide by 2 pi. This is the correct normalization. So this one here in H2 XR. So this is the RAM cohomology of closed real 2 forms, modulo exact real 2 forms. This is independent of G, and of the choice of G. And this is denoted by C1 of X, the first Chern class of X. So yes. So the factor of 2 pi is there for normalizational reasons, but it's you don't have to put it if you don't like it. This and yeah, should be good, no? 1 over 2 pi should be the usual canonical normalization, and so we can now say what CalabiYau means. So X is called CalabiYau or CalabiYau manifold. If X is a Comper complex manifold, which admits some Kähler metrics, which has a Kähler metric, and the Sverchern class is 0. Yeah, perhaps I didn't remark earlier that these scalar metrics do not always exist, unlike the Hermitian ones. However, all the examples that I gave already give you a really rich family of examples where you do have scalar metrics. Yes, and also I should warning, this is not, may not be the standard definition. This Calabi-Yau word in the literature does not have a well-defined, does not have a unique definition, unique meaning in the literature. So every time you see something about Calabi-Yau, you should actually check which definition they're using. This one is probably most people here would actually disapprove of this. So this is the most liberal definition of Calabi-Yau. Usually one imposes some further restrictions that make the class smaller. I actually like this one because this, as I would say, that's where the Calabi-Yau theorem applies, the largest class. So it's kind of natural. And so here are some examples of Calabi-Yau manifolds. So the first simplest ones are just Torai. So I take Euclidean space and I mod out by the action of a lattice. Here lambda is a lattice, isomorphic to z to the 2n inside Cn, which acts on Cn by translations. So it's just a Euclidean space mod out by translations. And topologically, this is diffeomorphic to product of circles. The simplest example would be to take C, and here is the lattice lambda is generated by these two vectors, say, and then you just draw this would be the fundamental domain, and the lattice lambda continues. These are all the dots are the elements of lambda, and after you quotient out, you can see here this is topologically a torus. And however, it's important to realize, if you've never seen this before, that if you change the lattice lambda, it's always diffeomorphic to the same manifold, but these manifolds are different as complex manifolds. So two complex manifolds are the same if you can find a holomorphic map from one to the other, which is bijective, and we say isomorphic. And when you vary lambda, in general, you don't get isomorphic Torai. So there are a lot of Torai. And these are Calabi-Yau. In fact, if you take the Euclidean metric on Cn, that just write down the obvious coordinate with Gij var, for example, the identity matrix that has constant coefficients. So certainly scalar, the derivative is 0, and it's certainly invariant by translation. So it descends to a scalar metric here. And since it has constant coefficients, when you take two derivatives for the Richie, you still get 0. In fact, the whole curvature vanishes. So the first class is 0. Much more interesting are hypersurfaces in CPN. Say in CPN plus 1, where P is a homogeneous polynomial of degree n plus 2. And again, assume that it's smooth. So this is a complex hypersurface. It's a real codimension 2. And this is Calabi-Yau. Calabi-Yau. This is a standard calculation, but not completely trivial. And it's also, as you raise n, when n is equal to 1, you do get indeed a torus. But when n is equal to 2, this is not a torus because it's simply connected. And these become actually Calabi-Yau in whatever strictest sense you want, as long as n is bigger than or equal to 2. Okay, so these are actually correct examples. And when n is equal to 2, there is, in fact, in some sense, a classification of these Calabi-Yau manifolds. So X Calabi-Yau of dimension 2, complex dimension 2. Then X is isomorphic to either a torus, a 2 torus, so C2 mod lambda, or a K3 surface, where K3 surface by definition means simply connected Calabi-Yau surface, or a finite quotient of one of these two. So there's one of these with a finite group acting freely in a holomorphic way, and then you take the quotient, so or a finite étale quotient of these. And these quotients are also completely understood. So there are a lot of Torai and also a lot of K3 surfaces. So this gives you a lot of examples, but they are in some sense understood. Okay, so the nice thing about Calabi-Yaus, so for now, what you should take out is that you have all complex manifolds, a smaller class of the Kähler ones, and then an even smaller class of Calabi-Yau. So it's just one particular class of complex manifolds, which happens to have really nice properties, which I now describe. So this theorem of Yau, or also known as the CalabiYau theorem, says the following. So if X is a Calabi-Yau, and omega is a Kähler metric on X, then there exists a unique omega tilde, which is also Kähler metric. So you see I already use omega instead of G, such that, first of all, they define the same cohomology class. And second, the Richie curvature is identically 0 everywhere. So you can find these Kähler metrics, which are Ricci-flat. So these are Ricci-flat Kähler metrics. So this was a bit of a shock when it happened many years ago, because first of all, these were the first examples, gave the first examples of compact Riemannian metric, which has Ricci 0, but it's not flat. So not the whole curvature is 0, but only the Ricci. So that there weren't any known examples before this theorem. And the example that works, you just take a K3 surface, and it cannot be flat for topological reasons. The Euler characteristic is not 0. And also, these Ricci-flat metrics are interesting, for example, because what's called the holonomy, in fact, it's the restricted holonomy, is contained in SUN. So this would be the holonomy of omega tilde, of the metric omega tilde. So the holonomy is what you get when you take a loop. Restricted means it should be null homotopic, and take a vector and take a parallel transport using omega tilde, the Riemannian metric of omega tilde. And then when you get back to the base point, the vector has changed. And by some element in general would be for Kähler metrics in the unitary group, and now it's in the special unitary group, which is more special and interesting subgroup. And if often you can make it equal, it's not hard to arrange that it's actually equal. And for this reason, these were very interesting for physicists, at least a long time back. By the way, if n is even and the holonomy is actually equal to the SP n over 2, the symplectic group, then we will call it hyperkähler, G tilde hyperkähler metric. Or perhaps you should say contained. It depends on the definition. Say equal, I will call it hyperkähler. And the example of hyperkähler is the K3 together with any metric given by this theorem. We may return to this hyperkähler later in the talk. Let's see. And these metrics that you get from the theorem, interestingly, are essentially never explicit. So of course, on the Torai, you can guess these metrics here must be flat, and therefore they must come from a Euclidean metric on Cn. So on the Torai, you can write them down by just writing down constant Euclidean constant coefficient metrics on Cn. But as soon as the Calabi-Yau is not a torus, even if the Calabi-Yau is explicit, for example, you just write down one polynomial, then there is no formula or explicit construction of these metrics. So it doesn't come out by solving some ODE or something, but or some ansatz in general, but it comes out of solving a PDE, and the solution is usually impossible to write down by hand. So in fact, there's even a problem that you can try to formulate correctly, I don't know, of writing down one of these metrics on K3 surface explicitly, whatever explicitly means. And after you formulate the problem properly, it becomes really interesting. And as far as I understand, it's still open. Yeah, so explicitly, I believe not, yes. So it's related to this instant on correction, wall crossing formulas that we heard a lot about in the workshop. But anyway, so next, the problem that we're interested in. So this is just the Calabi-Yau story, very brief introduction. So what you see from what we said so far is that the first chunk class, which anyway is 0, was independent of the choice of metric. Next, you can look at the cohomology class of the metric of omega. So the cohomology class of omega, this is not fixed in general. I mean, it's not predetermined. So this one here can vary inside the following parameter space Cx. So here, these are all the classes alpha in H11. I need to explain this one, such that there exists some omega Kähler metric on X with this class. So here H11 is the cohomology group of the subgroup of classes which have a representative which is a closed 1-1 form. So these are classes with a 1-1 representative. So it's the finite dimensional vector space inside this guy. And of course, the class of a Kähler metric is always in this vector space by definition. And you look at all the possible ones that you get. And this is Cx is is an open convex cone in this H11 called the Kähler cone of X. And it's, in general, a really interesting object to study and quite mysterious, in fact. In any case, even this talk, it will always look like this. There's just a two-dimensional vector space, and here there's a cone. So this picture may be misleading. The cone is here. For example, when H11 is dimension 1, then it's just a line, and the Kähler cone is just a half line. But I don't draw it, so that case would be essentially trivial in this talk. And the boundary, since it's an open cone, the boundary of the cone is not part of it, and it's actually what I'm interested in, at least what I will explain in this talk. So first of all, naive question is, what kind of information does this class tell you about the metric? So you have a metric, Kähler metric, and then you compute this class, which is some object in a finite dimensional vector space. So what does it know about the metric itself if you just take the class? So what information does the class give about the metric itself? In fact, quite a lot. So the observation, again, really basic observation, is that if I have a V inside X, which is a complex submanifold, these are defined exactly as you define real submanifolds, but using holomorphic defining functions of dimension k, say positive, then I can integrate over V. I can integrate the wedge product of omega with itself k times, which I denote by the power. And if I divide by k factorial as a normalization factor, then I get the volume of V with respect to omega. Maybe I call it G. So this would be the 2k dimensional volume. So the volume of this complex submanifold can be, in fact, computed by this integral. And the key point is that by Stokes' theorem, this integral only depends on the cohomology class of omega. So it's the same. I will actually denote it in the same way. But maybe you should write some pairing between this cohomology class, the cup product, and the fundamental class. In any case, it's by Stokes only depends on the cohomology class. So if you know the cohomology class, then maybe you don't know exactly the metric, but you know exactly all the volumes of all the submanifolds. And also more generally, the same is true if V is slightly singular for V analytic subvariety of X. So I'll be just vague about what analytic subvariety means, but morally it's just the same as what I wrote earlier, something which is locally given by finally many equations, which are now supposed to be just holomorphic functions. So some closed subset, which is locally cut out by holomorphic, finally many holomorphic functions, that's an analytic subvariety. And if you assume that it's, say, irreducible, so you cannot write it as a union of two other subvarieties, then you can make sense of this integral, by integrating over some open part of V, and it's again cohomological. So I don't give any detail here, but when later I will, to be precise, I will say analytic subvariety, you just think of a complex submanifold, compare complex submanifold. So these are maybe singular, but they're slightly more general objects. Okay, so then, so now we get to the metric limits of Calabi-Yaus, at least the ones that we consider in this talk, are the following. So yeah, still here, the picture. So if I pick any class in the Kähler cone on a Calabi-Yau by this Yau's theorem, there is a unique representative of this class, which is Ricci-flat Kähler. So if you now change the class, either by a sequence or a path, maybe I just take a path, then you get a corresponding sequence or path of metrics. They're each uniquely determined. And you can study what happens when you do something like this. So if you degenerate the class to the boundary, what happens to the metrics? So this will be one of the questions that we will discuss now. So let's say a path. So let's suppose we are given a path, alpha t. So t is between 0 and 1. So alpha t are inside the Kähler cone for t positive, and alpha 0 is on the boundary of the Kähler cone, like this. The path would be, say, continuous, if you want. But it doesn't have to be a path. You can just take a sequence. And so let an omega t for t strictly between 0 and 1 be the unique Ricci-flat Kähler metric. We just write RFK in the class alpha t. Again, t is equal to 0 is not allowed. Then the question is, what happens, or what is the metric limit to x omega t as t goes to 0? So this would be the question where you fix the complex manifold, or fix the complex structure, and you vary the Kähler class, or the cohomology class. There is also the kind of a dual or mirror or whatever. Another question where you do the opposite, where you fix the Kähler class and vary the complex structure. And if I have time, I'll mention it at the end. For the workshop participants, the other case was discussed in great detail by many people during talks. In any case, I will say something at the end. So I'm trying to cover something that was maybe not exactly done already. Also in this case, this is the case where actually we can say a lot, as opposed to the other case where it's mostly conjectural. So so what happens, so this, of course, if you think about it just from the Riemannian geometry point of view, just forget about the complex manifold part. These are just sequences of Riemannian metrics, which are Ricci-flat. So this is in particular Einstein metrics. Einstein means that Ricci is constant. And there is a huge literature about the limits of Einstein metrics. In particular, results that are relevant are in the 80s, Mike Anderson here, and Bando, Kazuya Nakajima, and Tian. I will also mention some other names later. So this is in the 80s, 90s, and then Shiger Holding, just put a few names, around 2000 or 90s, 2000. They developed a rather extensive theory to study limits of Einstein metrics or even more general metrics, but from the point of view of metric space. So you forget even that you have a manifold at all, and you just keep the metric structure, the structural metric space given by the distance function of a metric, and then study the regularity of the limit. So this theory here, actually, we are not going to use at all. Or no, we will use it, but in some tangential way. So what we want is to gain a better understanding using the fact that these are Kähler compact Calabi-Yau, so you have a lot more structure to work with. So as I said, so there are two useful geometric quantities from, again, the Riemannian geometry to consider are, first of all, the total volume, so vol of x. As I said, this is just computed by some cohomological integral like this. So this is the same as this integral of alpha t. And certainly this converges to the integral of alpha 0. Can I use this integral notation for the homology, pairing of homology and cohomology? And this number here certainly is non-negative, being a limit of positive numbers. Could be 0 or could be positive. So we will discuss this in a second. This is one. And the second one is the diameter of x omega t. So this is the, I just tried to say it in words. So you have this metric omega t, or if you want the Riemannian metric gt, so you can measure the length of curves in the usual way by integrating the length of the tangent vector, and then you can define the distance between 2 points in x as the infimum of the length of curves, say piecewise smooth curves that join the 2 points. This defines a metric space structure, and then the diameter is just the sup, in this case, the maximum possible distance between any 2 points. Okay, so how far from here to here? The distance between these two would be the diameter. Okay, so how distant can 2 points in x be when you measure a distance using GT? So the first theorem or remark, which again does not follow from this general theory at all, is that so this uses the complex structure and this additional structure. So this I proved, and also independently Yuguang, Zhang, who is also here. This is quite a few years ago. Then in this setup, we have the diameter is uniformly bounded above. So for all t 0, 1. So there is some constant c so that the diameter does not blow up. So this is not too hard, but you need to combine, as I said, different ingredients. And it's good because it somehow says that this manifold cannot stretch out infinitely. So the second thing to look at is here the volume, right? So the volume can go to 0 or not, and you can detect it just by computing this integral in the limit class. So if the integral of the limit class is positive, then we'll say that we are non-collapsing. I should say volume non-collapsing, but it's actually equivalent to whatever other definition of non-collapsing you have in your mind, and otherwise collapsing. And this second one is part of the title of the workshop, right? So I should talk about it soon. But first, let me talk about the non-collapsing, which, as maybe you guessed, is much easier. It's much easier to deal with than collapsing. So yes. Depends on alpha naught, but actually in a rather weak way. Yes. So it depends on alpha naught and also on the background geometry, if you want, on a fixed reference metric. And it depends on alpha naught, but actually only in a very, very weak way. So the dependence is quite explicit and quite nice. Yeah, that's right. So in fact, as long as alpha naught stays in a fixed, if you vary alpha naught inside a fixed compact set, that constant does not blow up. It only blows up if you move off to infinity like this, which it does, it must in general, because you can just rescale the metric by a huge factor. Okay, so let's look at this case first, non-collapsing case. So the volume of the total manifold does not go to 0. Then you can look at the subvarieties, what I said earlier, right? So if you look at the union of all subvarieties, the irreducible analytic subvariety, again, just replace complex submanifold such that the integral over V of alpha 0 to the dimension of V is a 0. So a subvariety like this is exactly one where the volume of V, the two-dimensional volume of V with respect to omega t goes to 0, as t goes to 0. Okay, so you take all the subvarieties which are shrinking, and it's not, X is not part of this, and you call it a null of alpha 0, the null locus, alpha 0. This is something that came up first in algebraic geometry. I'm not quite sure who first, but certainly Michael Nakamaye studied this explicitly, Sean Keel also around the same time. And pictorially, you have here, I'll give an example very soon. So this is the parameter t, t equals 1, t much smaller than 1, and then what we would like to say is something like this, t equals to 0. So at least their volume is going to 0. The theorem is this. So combination of, again, of theorems of a bunch of people. So myself, then Rong and Zhang, and finally an improvement with Collins. So this last improvement was done more recently, but these were a bit earlier. So again, X Calabi-Yau, alpha 0 on the boundary of a Kerr cone with positive integral. Then there exists omega 0, incomplete Ricci-flat Calabi-Metric away from this null locus. Oh, I forgot to say, the null locus is not all of X, thanks to our assumption. I mean, it's a really big union a priori. It would be huge, but it does not fill the whole of X. And in fact, I should remark, this is not big at all. This is itself an analytic subvariety. So although it's a really big union of subvarieties, in fact, most of them are contained in some other one that also contributes. So in the end, you just get a subvariety overall. And it's a proper analytic subvariety. So this is a very small subset. And on most of X, so exactly away from this, you have a Ricci-flat Calabi-Metric, which is not complete. This is in the sense of Riemannian geometry, that there's some Cauchy sequence that does not have a limit. And such that for any path alpha t is above, and the matrix Ricci-flat Calabi-Metric is above, we have that these converge to this smoothly. So omega t converge to omega 0 smoothly on compact sets of this X minus null. So smoothly just as tensors in the most naive possible way. This is as t goes to 0. And globally, if you regard these as metric spaces, they converge as metric spaces to the metric completion of this nice limit. So this is the metric completion. So as I said, there are some Cauchy sequences that do not have a limit. You throw in the limits, define the metric completion, and this is as metric spaces. So technically, it's called the Gromov-Hausdorff convergence. It means that you really just regard them as metric spaces, and there is a natural notion of convergence of metric spaces to a limit. So, so you have, by the way, this null alpha 0 is also the smallest possible set where this occurs. This is completely sharp. You cannot have this convergence on any strictly larger set. So this is the largest possible set. So X minus null is the largest possible set. So the picture is like this here. So on this region, you have nice smooth convergence. And then as metric spaces, you obtain a compact limit. This is a compact. I didn't say it, but it follows from the diameter bound. And something bad happens here. So let me give an example.
Complex structure. The complex structure on the limit on the.
Oh, this is a different question. So if you in general, you need some assumption. For example, you should assume, say you assume that this class is rational, so the whole setting becomes algebraic. There's a line bundle. Then you do have a map, a holomorphic map from X to Y, where Y is some singular in general, so a new variety with a different complex structure. And then it's actually true that this metric completion is homeomorphic to Y. And this was proved by Jan Song following work of Donaldson and Sun. So I didn't write it, but that's true if you assume that it's projective. Somehow if you can obtain this complex analytic map. And certainly you can hope that it's true in general, but that's really not clear. I mean, should be true. In general, in this setup, there should be a holomorphic map that contracts this null down, shrinks it down to a new singular, possibly singular variety, which should be homeomorphic to the limit. But the construction of this map seems rather far off, even in dimension 3. Yeah, so in some sense, yes, you do get a new complex structure and probably singular. And the example, the standard example of this picture is the so-called Kummer construction. So X equals the Kummer K3 surface, which I can now describe. So you start with a T, just a 2 torus. You look at the involution, which maps Z to minus Z. So here I'm using Z as a vector, ZW to minus Z minus W. And take the quotient Y. So this action is not free. This has 16 fixed points. And the 2 torsion points of this torus. So this quotient has 16 singularities, but they're of the mildest possible type, orbifold or rational double points. And you can resolve them by what's called a blow-up, say F, pi, F. Resolution, this is the blow-up of the 16 points. It's just a way to replace the singularities with the smooth manifold. So the preimage of the 16 singular points, this is, I guess I only draw 2 here. This is F. So here, F inverse of the singular points is a disjoint union of 16 spheres. Actually, I should write CP1s. CP1 is the same as S2. And they are in here. And X is a K3 surface. K3. So it's a smooth Calabi-Yau, simply connected. And then in this Kummer construction, I can take alpha 0 to be the pullback of a Kähler class on Y. So here omega Y is Kähler on Y. I know Y is singular, so what is a Kähler metric on Y? That just means a Kähler metric on the torus, which is invariant under I. And you can define the pullback, it's no problem. So this class here indeed is on the boundary of the Kähler cone. Indeed has integral of square positive. And the null locus is this method, let's call it E, the exceptional divisor, that's the technical name. Okay, so then what the theorem says is that you have, if you take Kähler classes on this Kummer K3, for which the volume of the sphere shrinks, then you get limit incomplete Ricci-flat Kähler. In fact, in this case, would be flat. Omega 0, the limit would be just a pullback of a flat Kähler metric on Y. I should say orbifold Kähler metric on Y in this class here. So the whole curvature disappears. It concentrates around the 16 points. And this was already known. So this was proved earlier by certainly, so Kobayashi, R. Kobayashi and Todorov, and I think also by Lebron and Singer. Is that right? These proofs are different. So I believe all 3 proofs are different, if I'm right. So these 2 and this proof, they're all different. So this one I think is a gluing construction. This one here uses the Torai theorem of K3s and some ad hoc arguments. And this is a special case of this higher dimensional general theorem. And OK, so this is the non-collapsing case. I shouldn't say it's completed, because there are still a lot of things we don't know. One thing is what you just asked about whether the limit is an analytic space, and the other thing is what are the bubbles. So if you zoom in near this null locus, if you zoom in fast enough, you get an limit which is non-compact, and then you would like to know more about these bubbles that are forming. And while in this example we know exactly, thanks to these people, that does not follow from here at all. So in general, you cannot really hope to classify these bubbles, but at least to say something meaningful about them would be nice. Okay, and then the collapsing case. I guess I'll be brief. So you want to find, first of all, examples. Say it's just very simple-mindedly. Here, actually, as I said, the examples are not so easy to come by, right? You need to perform this Kummer construction. This is certainly the simplest example you can find. However, for the collapsing case, it's much easier to find examples. So here you want example of this X Calabi-Yau and alpha 0 on the boundary of Killer cone. Say not the 0 class with the integral of alpha 0 to the n equal to 0. Of course, the 0 class is fine, but some other example. So, but of course, what you can do is just take a product and pull back from one factor, right? So, so if you just take X to be, say, Y cross F, where F is Calabi-Yau. So these have different dimensions. So these are both positive dimensional, the base and the fiber. And I take alpha 0 to be, so this maps to, say, Y, where this one here, say, F, whatever the projection map. And alpha 0 is the pullback of a Kähler class on Y. Then it works. So you pull back a Kähler class from some lower dimensional space. It's automatically on the boundary, and it's not 0. And this satisfies this. So this would be the kind of trivial product example. And in fact, it's not trivial at all already in this case. And you can try to generalize this to fibrations. That's what I want to do here. So let's assume that we have a fibration structure. So assume that my F, that I have a holomorphic map. So this was n-dimensional. Now this is m-dimensional, where Y is, again, compact Kähler of lower dimension. Let's say positive and lower dimensional. And this F is a surjective holomorphic map with connected fibers. So such a gadget is usually called a fibration or fiber space. We will just take, again, alpha 0 to be the pullback of Kähler metric downstairs. And then, again, it's correct. So you do get that alpha 0 is on the boundary. It's not trivial. And the integral to the n is 0. So the interesting bit is that modular deep conjecture in algebraic geometry, this should be the general case when alpha 0 is irrational. So of course, I'm cheating because Y need not be smooth. So if alpha 0, as above, is in fact rational, then we expect, so a conjecture has a particular corollary would have that there is such a fibration. Y will not be smooth, really, but apart from that, it's exactly what you get here. So in the irrational case, it's totally false, just on the torus. So in some sense, you are studying the general rational case, but a modulo the conjecture. In any case, you can assume you have this fibration. And then if I let, say, S prime to be the critical values of F, this is a proper analytic subvariety in the base, so small, and S to be the preimage. Proper analytic subvariety here, so small. And F, if I remove these two sets, this becomes a submersion. Submersion, which implies that the fibers xy, preimage of y, for y in this regular good part, these are all are a compact Calabi-Yau of dimension m minus n. So the Calabi-Yau is automatic, is inherited from X. So in other words, my manifold is like in that example. It has a fibration onto a base, and the fibers are Calabi-Yau. So like this. This would be S, the kind of singular fibers, let's say, naively. and the smooth fibers are pictured as Torai. You should think they're actually Calabi-Yau, may not be Torai. And of course, the example of these fibrations, apart from products, which I already discussed here, the really nice example are K3 elliptic fibrations, say X K3, Y is as a sphere, and F elliptic fibration, meaning it's like here, and the generic fiber is a torus of dimension 1. These exist in great abundance. They're easy to find. And whenever you have one of these, you're exactly in this picture. And the base is a sphere. And the set S prime here would be finite. And the singular fibers are, in fact, also in general known, like what they are. Maybe as a side remark, I mentioned this theorem with Yu-Guang, that if you have such a fibration, if f x to y, such fibration with S empty, so in other words, a submersion everywhere, then it's a fiber bundle. F is holomorphic fiber bundle. So if there are no singular fibers, the family is locally trivial in the holomorphic sense. So it's not really important for this discussion. It's just to say that if you want interesting examples, you have to allow singular fibers. So the theorem, what we have is the following. So again, this would be the last theorem and a collection or a compilation of results. So let me try to write down in the too many names. So me, then with the Gross, Zhang, yes, also earlier Song and Tian, and me with Ben and Yang, Ben Weinkov, and also with Zhang and with Hein. Sorry, too many papers combined in one theorem. So if you have a fibration as above, this fiber space, and the alpha t, you take it to be this alpha 0 plus t omega x, where these are Kähler metrics on the base and upstairs, and t is between 0 and 1. And omega t, the Ricci-flat metrics as before. So then what you get is that, so note that I'm just taking a straight line. So then there exists omega 0 Kähler metric on the base minus this discriminant locus with Richie not quite a 0. This non-negative equal to something called the Weil-Petersen form. Maybe I'll explain later what this is, such that omega t converge to this pullback locally uniformly on this locally on compact sets of x minus s as t equals to 0. So in the C0 topology, and maybe go to here. Also, in fact, smoothly, if the xy's are a Torai or finite quotients of Torai or quotients. So this can be improved to smooth. And also, if you perform the following, I'll draw the picture now, but if you perform the following rescaling, omega t over t, restricted to the fiber, so this class here is in a fixed class. On the fiber, this dies, and you divide by t, and this converges, again, smoothly on the fiber to the unique Ricci-flat Kähler metric on the fiber, which is Calabi-Yau in the restrictor class as t goes to 0. So the picture is like this, here like this. So if I go approach 0, the manifold is shrinking, at least away from the singular fibers. The volume of the fiber is going to 0. That's what these classes are doing. and the metrics, in fact, shrink. The fibers are shrinking uniformly. In the limit, you get this pullback from the base, at least away from the singularities. And if you magnify by 1 over t, then the base grows, the fibers remain of a fixed size, and what you see is, in fact, more is true. What you see is a product. If you rescale away from the singular fiber, I didn't write it, but what you see is the product of a Euclidean metric in the base and this Ricci-flat on the fiber. So I should say that all this, and in fact more, was proved when X is K3 and Y is P1, so in the elliptic fibrations, in a really nice paper by Gross and Wilson in 2000. This was the motivation for our work. So this is a generalization of Gross-Wilson in higher dimensions like this. Maybe I should say who proved what. I don't know, it's a bit long. So in any case, the final results. So Song and Tian did something in the case, again, they found a new proof of some part of Gross-Wilson in this case. This I generalized in the T to higher dimensions, and then with Mark Gross and Yu Guang, we did the case of Torai fibers with an extra assumption that was removed with Hein. And then with the Ben and Xiaohui, we proved the main chunk, and the part of it is improved with Yu Guang, so quite complicated. And well, I guess in the last -1 minute, I will just say that this is related to the mirror symmetry that I put in the abstract, but I don't have time to mention. Namely, but in the case of K3s or hyperkähler, which is not the interesting case, I suppose. So when you're K3 or hyperkähler, you can take this setup and sort of hyperkähler rotate it to the other setup that I mentioned very briefly earlier, when the complex structure is fixed. Sorry, the Kähler class is fixed, and the complex structure degenerates. And the limit is supposed to be a large complex structure limit, maximally degenerate, degeneration of Calabi-Yaus. So only in this hyperkähler case, and with some additional assumptions, then this theorem, in fact, tells you what the limit is, what the metric limit is under this different type of degeneration. So these results have some bearing on this mirror symmetry, but only for the hyperkähler case by cheating by this hyperkähler rotation. So it does not say anything in the other setup, in the case of CalabiYau threefolds, for example, which is the physically relevant case. Anyway, thank you very much. I'll stop here.
Questions, comments?
I was wondering if one, so when you look at this kind of irrational collapsing case where the prototype would be take a torus,
Right.
have a class that's collapsing along a foliation.
Right.
Irrational perspective.
Yeah.
And you could do the same thing on a Kummer built out of that.
Right.
Is there anything that can be said about the existence of foliations or something so in this very nice rational case that you described, right, you actually get a map to a lower dimensional variety. But is there anything that you could say about the existence of foliation in greater generality?
No, it would be really nice. So no, I cannot say anything, but certainly one can dream of the following, that the Ricci-flat metrics, when you approach one of these irrational limits, converge as tensors, perhaps say smoothly, dream away from some subvariety. So the smooth limit would be a semi-positive definite tensor. And so you can a closed semi-positive one-one form. And the kernel of that defines a foliation, which has complex leaves, but in general is not holomorphic. It's not a holomorphic foliation. Modulo this initial dream, you should get a foliation. And if you dream even more, perhaps it is true that it's in fact holomorphic. And this was proved by Weidong Ran if you assume curvature bounded, which I didn't have time to say, but essentially it only happens when you have the fibers are Torai. And in the fibration case, yes. So with a lot of imagination, yes, you should be able to construct a foliation, but I doubt that you can really carry out any of this. It's probably better to assume, as you said, that there is a foliation, like take the torus and then see what happens. And even this, I don't know how to do, so that's really hard. Yeah. But yeah, certainly it's related, expected that you should be able to abstract a motion per foliation out of these irrational limits. Yeah.
Any other questions?
Okay, that's fine for me. No.
Thank you.